Hi everyone, welcome to machine learning using Python. This is support vector machines module 8, third session on that third module, basically third presentation or third part we call it. It's session number 16. The total is 24 sessions. We are on the 2/3 today. So we have completed 15. This is session 16. And Jamit Wasawa has done a fabulous job. And we look forward to hearing from him about the machine learning using Python, the support vector machines, especially the kernel tricks, which are one of the popular ones of the last decade. And so before we move on to the use cases, we wanted to complete this in a thorough way. So I'll hand over to Jamit Basawa, our instructor. Hey, welcome, Jamit, and go ahead, take the floor is yours, and you can present this in a very methodical way as you always do. Thank you.
So thanks a lot, sir, for the introduction. So hi everyone. This is machine learning using Python, and we are discussing support vector machines since the last two sessions. This is the third session on support vector machines, and total it's a session 16th. So the learning objective for today's session is going to be kernels. We are going to discuss kernels. Why do we need kernels? What are kernels? When do we use the different types of kernels? So you can see the list. They are listed out over here. The four of them: linear, poly. So linear is for linearly separable, but poly is the name. Polynomial is the whole name. Whenever you are able to represent the relationship in a polynomial terms, and that is the time when we use poly. Then radial basis function, RBF kernel, and sigmoid for a sigmoid kernel. So these are the kernels that we are going to use today or discuss today. First, just a very short recap of the support vector machines. What are they? They are supervised machine learning algorithm that classifies data by finding an optimal line or a hyperplane that maximizes the distance between each class in an n-dimensional space. Support vector machines were developed by Vladimir Vepnik and his colleagues, and he's published it in the paper titled Support Vector Method for Function Approximation, Regression Estimation, and Signal Processing in 1995. So you can see the pictorial representation of support vector machines. If we go for the image on the left, you can see that there is a hyperplane which is mathematically represented as a y equals to wx plus p. And you can also see the data points which are containing which are belonging to two classes, red and blue. I will not say the label names right now. They belong to two classes, class 1 and class 2. So, and also parallel to the hyperplane, there are two parallel lines which goes in parallel to the hyperplane, which are called as margin lines. Now these margin lines are defined by the support vectors. Support vectors are the closest points to the hyperplane, which also define the orientation of the hyperplane. So these margin lines passes through the closest data points that are present to the hyperplane. And based on that, the hyperplane divides or separates the data points in two classes and creates a separation. You can see that these are linearly separable because we are able to find a space where data points can be linearly separated. And when the margin lines are there, we try to make them as large as possible. Now that was the recap of SVMs. Now, how do SVMs work? If we connect to the previous example, the previous example was based on linearly separable data. That means that we were able to create a hyperplane in a space where the data separates from each other. So the first graph uh, represents that linearly separable data, or a SVM working with linearly separable data. Now, when we talk about the non-linearly separable, you can see that in graph 2, we are not able to, or the graph on the right, we are not able to create a hyperplane which separates the class 1 with class 2, or class red with class green. So in such cases, what we do is that we use transformations of data to map them into higher dimensional space and create a hyperplane where we are able to separate them. And for that use of transformation, kernels are used, which is the topic of discussion today. So, starting with our first kernel, the linear kernel. So, what is a linear kernel? It is the one of the simplest form of kernel function that we use for linearly separable data. It represents a straight line in the 2 dimensions and can be represented mathematically as the dot product of the 2 vectors. So when we use a linear kernel, uh, when of course the data is linearly separable, then higher dimension spaces where a number of features are greater than the number of samples, then computational, when we are looking at a solution where we want computational efficiency. So because it is computationally efficient because it does not need the transformation that is needed in the nonlinear data type. So a simple example for a linear kernel is think of a scenario where 2 types of fruits are laid out on a table and can be divided by a straight ruler. Linear kernels are also simplistic. It's efficient for data with many features but fewer data points, like a high dimensional space as mentioned before. And it's straightforward. So that's why they are uh, computationally efficient. Now, that was about linearly separable data. The linear kernels deals with linearly separable data, but the non-linearly separable data is something like this. And this is what the transformation that we were talking about. So you can see that in the graph on the left is we can say that will not be able to create a hyperplane in this graph, and as the data is not linearly separable. Now what kernels are used for is to transform these data points which are appearing on the graph on the left, to transform them into higher dimensional space, to transform them in such a way that we are able to create a hyperplane which separates those data points after the transformation. So you can see that a 2D graph is converted into a 3D graph now. And uh, in a 3D space, we are able to create a hyperplane which separates the red class from the green class. So that is why the kernels are used. So discussing our first kernel, which is the polynomial kernel, it allows the curved decision boundaries and is defined by a polynomial equation. Mathematically, it can be represented as a gamma into xi uh, t for the matrix transformation and into xj. So it's a dot product plus r and the whole term uh, with the power of d. So where d is the degree of the polynomial, gamma is the scaling factor, and r is the constant term. Xi, xj are the data points or the feature vectors. So when we use polynomial kernels when we are able to define the relationship of the data points in a uh, with the help of a polynomial. So, so between the nonlinear and can be represented as polynomial functions. So customizing the decision boundaries, it allows flexibility in shaping the decision boundary through a degree parameter. Uh, you you can adjust how curvy the decision boundary is by using a parameter called degree of the polynomial. So you can think of it as adjusting the curvature of the road. Then the moderate complexity. It is suitable when the data set is not too large, as higher degree polynomials can lead to a problem of overfitting. So our third type of kernel is a radial basis function kernel, which is also a go-to kernel when we are working with SVMs, and if you want to just try out the SVM for on a data set, then popular choice is RBF. Mathematically, it is defined as the exponential term for minus gamma and the Euclidean distance between the two vectors. So in the expression, the 2 is actually the power of the Euclid for calculating the Euclidean distance, and it's not a multiplication with 2. So just so we calculate the Euclidean distance between the two feature vectors. Then you can see that there is a minus sign for the in front of gamma, which ensures that the value decreases as the distance increases, reflecting that the similar points are closer together. Uh, so they should have a higher similarity score. Now the parameter gamma, it controls the width of the RBF kernel. So the larger gamma results in the more localized kernel, meaning that the points need to be very close to each other to be considered similar, and a smaller uh, value of gamma makes the kernel broader, allowing the points further apart to still be considered similar. Now, the exponential function maps the squared distance to a similarity score between 0 and 1. So that was about the bit of on the mathematical reasoning of the expression. When do we use it? We use it in a non-linear data, as the RBF kernels are used for data leading to nonlinear, which have nonlinear classifications because it allows for a more flexible decision boundaries. It captures the similarity between points based on their distances in the feature space with the gamma parameter and controlling how sensitive the kernel is to changes in the distance. And the kernel also efficiently transforms the input space into a higher dimensional space, making it easier to separate the classes in the complex data sets. So apart from that, the journal purpose, because it can handle variety of data shapes, and they are sensitive, the sensitivity to the hyperparameters. It requires a careful tuning of the gamma parameter, and it can lead to uh, overfitting as well. And too low of the gamma value can lead to underfitting as well. So moving to the our fourth kernel is so our fourth kernel is sigmoid kernel. It so sigmoid is also used as a activation function in the neural networks. So it resembles that and is defined by 10h into gamma xi and the transformation of the matrix X. So basically a dot product of xi and xj plus r. So here the parameters are gamma and r, and it maps the data into hyperbolic tangent space. So when do we use the sigmoid kernel? Uh, in When we are trying to have the neural network like behavior. So you using the sigmoid kernel when we want to decision boundaries similar to those that are found in neural networks. It can capture non-linear data relationships, but it's less common than other kernels. And parameter sensitivity, like the RBF had the parameter sensitivity. It requires tuning of parameters, and the performance can vary slightly depending on those settings. So
You
yeah,
are aware of sigmoid, right?
yeah, I'm on sigmoid one.
Yeah, okay, no problem. So maybe
Yeah.
you can explain what is sigmoid before you get into sigmoid kernel as a whole. Activation function, basically. Yeah, go ahead.
Yeah.
So what I meant is normally for the neural networks, you have different activation functions, right?
Yeah.
So sigmoid being one of the functions, and that's how that is related to kernel. I just wanted to realize that because usually you do a step function or you do some kind of a what you call other activation functions like whether you have a negative in them or not, whether they have only positive aspects of it and negative, because without negative you cannot get feedback, right? When you have
Yeah.
activation function. In any AI/ML you need a feedback. So for feedback you need to have some negative mechanism. So the linear, even if it is some kind of a non-linearity with some negativity,
Yeah.
then give us the, and sigmoid is one of the better ones to use. That's
Yeah.
what. So that's what I wanted to. And what is sigmoid kernel? I would like to hear from you. Thanks. Thanks, Jim. Yeah.
Yeah. So just adding a few points to what Professor started with. So activation functions in neural networks are basically, if you imagine uh, 3 by 3 square and divided into 9 parts. And if we are trying to locate a dot which is on the second, let's say going from left to right on just only on a second square, then the rest of the squares or anywhere on the square, any one of the squares, there is an activation function. Uh, so the neurons have to connect to those and also activate on the place where we are trying to find it, and not activate when they are not needed. So in order to learn the shape, if we go into the bigger picture, so basically activation of the neurons are needed in order to work with neural networks, and those activation functions, one of out of one of them is a sigmoid kernel. Sorry, not sigmoid kernel, but the sigmoid activation function. So the sigmoid kernel here resembles that. If we mathematically um, describe the sigmoid function, it's tan h into tan h of gamma into xi, the dot product of xi and xj plus r. The xit is the same reason for the matrix multiplication, basically having them into a scalar quantity. Now the gamma term in the mathematical representation, it scales the dot product. The larger the gamma gives more weight to the dot product, making the kernel more sensitive to the similarity between points. And conversely, if we use a smaller gamma, it results in the less sensitive kernel. And R here is a constant term that can shift the function. It adjusts the output of the kernel. So a positive R can make the kernel value more likely to be positive, while a negative R can allow for more variability in the output. So when we add the uh, tangent function, it maps the result into the hyperbolic tangent function between the range of -1 and 1. So it transforms the linear combination of the dot product and the constant r into the non-linear output.
So just to clarify, tan h is a inverse, right?
Yeah,
Tan,
it's a hyperbolic function.
basically
Yeah,
tan. So it's you put it as a tan h, that's okay. But essentially, these are all either you have a sine function for activation, you have a cos function for you have tan function, you have
yeah,
sig, you have, pulse function. So there are step function or some angular, so that there is a linearity change in non-linearity, linearity for the weight combination of the ability to stress certain area of the picture if you are doing some picture, object detection or uh,
yeah,
visual processing and all. So these are all mathematical and they have significance. We may not understand everything, but as long as you know that you can use the function and follow the process, you should be able to execute. So sigmoid kernel is one of them. And thanks for clarification, James. It was really good explanation. Thank you.
yeah. Thank you so much. So yeah, just a few points for the 10H. The so the value close to 0 indicate low similarity. The values close to 1 indicate high similarity, and the value close to -1 indicate that the points are clearly dissimilar. So as said, that the hyperbolic tangent function. So the range is between -1 and 1. Now, uh, getting further with the uses of the sigmoid function, sigmoid kernel. Sorry, I'm getting confused with the equation and stuff. So, so uses of the sigmoid kernel when we are trying to have a behavior like the neural network and having the boundary similar to that of the neural network, then when we use when do we use a sigmoid kernel is, of course, we are discussing it in the subsection of non-linearly separable data. So we use it in a non-linear data, and it's similar to the RBF, the sigmoid kernel. The parameter tuning is also sensitive. So it requires a tuning of parameters, and its performance can vary significantly depending on those settings. So, yeah. So just to summarize the uses and meaning discussed in a very short way. The kernel we started with linear, as it works with linearly separable data, and the meaning is a straight line. So a straight line dividing the classes of the data. For the polynomial or the poly function, it works with the nonlinear relationships, mode complexity. Then comes the radial basis function. It is a Gaussian function, non-linear data, and is used for general purpose, as its ability to work with a variety of data.
So,
Then,
maybe this Gaussian function is our continuous function, right? So the normal distribution, what we call, right?
yeah,
RBF is what R stands for?
radial basis function.
Radial basis. So you take a radial from where? From the bottom of the top of the or bottom of the Gaussian normal function. So is it like a vector going from center and rotating around all the Gaussian function from n degree to n degree or types of things? Or what is the radial about it?
So I I will. I haven't read about it, but the uh, it's a Gaussian function. So it goes. It's not inverse. It's the same as the normal distribution function that we
Correct.
plot the graph of.
That is
So
68% when
yeah.
we from
So
the top, right?
yeah, yeah,
So
yeah,
one standard deviation and three standard deviation, there is a difference.
yeah. Yeah, so it divide. If we go into the graphical sense and meaning of it, then yeah, we can divide the data that way if we connect the analogy that way for both of them.
So possibly the radial base function can be starting from the mean and
Yeah,
the radiation, send the standard deviation, one standard deviation, two deviation, three deviation, and
yeah,
part of the normalization or whatever the weight functions are there, they
yeah,
can be corresponding with that. So it may be angular rather than being straightforward, like we say 68% and 90, what is it? 95% and
yeah. The coverage of the data points and stuff.
so it's a basically weighing function, nonlinear data, and it's general purpose. Okay.
Yeah,
Yeah, go to the
yeah.
kernels. Yeah.
Yeah, so the uh, so on the sigmoid point, it's a hyperbolic tangent function with a range of -1 to 1, and we just discussed about it having an when do we use it? We use it for a neural network-like behavior, and the values of the tangent functions having close to zero, indicating low similarity, value equal close to one, indicating high similarity, and value equal to close to -1 for sigmoid kernel. function.
So you
And it
remember,
indicates
let me,
decimal.
what I
Yeah.
say is parabola, hyperbola, right?
Yeah.
Ellipse, parabola, hyperbola. Hyperbola is nothing but two like a tower, right? If you look at the tower, a chimney, not chimney, but the tower, usually is mills.
Yeah.
Uh,
Yeah.
so you see hyperbola, right?
Yeah.
So the hyperbola uh, at the center, if you look at it, it is a concave and convex, right? One side concave, the other side concave, but in between is your hyperbola, right? So
Yeah.
that area probably is being referred to here, and the activation function goes from center towards the edge at some angular. So it's a kind of a tan H formula.
Yeah.
That's why probably that is the reason they have called it hyperbolic term. Very
Yeah.
good. I think
Yeah.
it gives a very good meaning. This table is super. I think you got it right, and hopefully people will be able to understand and use it. Yeah, go ahead.
Yeah. Yeah. So after summarizing the kernels and their
Oh,
uses,
one sec.
yeah.
Hold. What did I do? I did something to the mic. Anyway, it doesn't matter. You continue. Sorry.
Okay.
Sorry.
Okay. Okay.
I
No.
thought I stopped the recording. No, I didn't. Yeah.
No. Okay. So after summarizing this, let's look at a small uh, program which uses uh, these kernels. So we are using the iris dataset. If you remember the iris dataset, just to okay, yeah. So if you remember the iris dataset, it's a common dataset used for uh, a very basic application of models. So this is how the iris dataset is. It has total 150 entries for three kinds of flowers having the class labels Setosa, versicolor, and virginica. And it contains the sepal length, width, and the petal length width of those flowers. And based on those length and width, we try to predict the class label over here. So knowing about the iris data, we import the necessary libraries first. Then we load the iris data and give the X and Y uh, split for the train and test of X and Y both. We create the parameter grid for our different kernels in order to use it further for the grid search. Using the SVC, which is support vector classifier, and using that model on our grid search CV, which with CV value equals to 5, fitting the data with the model and getting the best parameters and scores, printing those, and getting the classification report as well. So for the combination of wherever the C values were applicable, we use the value of 0.1, 1, and 10. We use the kernel linear, polynomial, RBF, and sigmoid, and the degree of 2, 3, and 4, which is only relevant for the polynomial kernel because it takes those values. And for gamma, which is for RBF and sigmoid, both of them, the first parameter is scale and the second is the auto. So running this, you will get the best parameters. You can see the best parameters that we have are C value equals to 0.1, degree equals to 2, and gamma set to auto, and the kernel is polynomial. And the best cross validation score is 0.95. You can see that precision recall and F1 score are all perfect, 1, 1, 1, 1. and the test accuracy score is also 1. When you want to so uh, to evaluate the model that we have created, we are simply using the confusion matrix, which will be on 3 by 3 in a square form. So the true labels are over here, which is on the y-axis, and on x-axis are the predicted labels. So you can see that almost all of the predictions are perfect for when we go for the best parameters. This is the confusion matrix that we got for the best parameters. But if we go for the individual predictions of individual kernels being used, so first for linear, it's predicting the best, giving true results and all the correct results. For polynomial, it's also giving us the correct results, 10, 9, and 11. Then for RBF, also it's giving all the correct results. But for sigmoid, you can see that it's not giving the correct results. Only for versicolor, it's giving us the correct results, whereas for Setosa and Virginica, it's not giving us. So as also mentioned in the slides, during the slides, that sigmoid function is not much famous, and it can be due to the simplicity of the data set and an overkill for the kind of function that we are, or the kernel that we are using. It can be a reason. But sigmoid can have its own different kind of application based on the data sets, as it is used when we are trying to have a neural network like behavior. So continuing, so today we discussed about the what are kernels. First we started with a small recap of SVM, then we discussed a bit about the linearly separable and non-linearly separable data. For linearly separable, we used kernel linear. Then for non-linearly, poly, RBF, and sigmoid kernels. And we used all four of them in a simple data set for iris, and got the performance of individual kernel as well as for the best kernels using the grid search CV. So this was it for the session on the kernels from SVM that are used in SVM. These are some of the references and data sets that can be used for learning purposes. So thank you. This was it, and also the references that are used. The last three references are combined. So these are all the references, not just specific to this one, but for all the references that are used for SVM. So thank you. This was it for support vector machines from my side. I hope it was fun to learn.
Yeah, Jamit, it was really good to understand the relationship between the activation function and the kernel function. And basically the non-linearity, usage of non-linearity for the identification of isolation of the classes for various images and objects and visuals and all that. That's the very good way of talking about supervised. This is a supervised learning, so you supervise and you get the best out of it for the class separation. And next, I'm just wanting to say that we can move on to the use cases which we had planned previously. So next two session, I think this is what today is Monday. So Wednesday and Friday, we
Yeah.
can on one use case, and maybe next week two use cases, and then we will get into some GenAI stuff. So that's the plan right now. So
Okay.
you can go with the two use cases which you have at hand. which we had included in the course, and start with those
Sure.
two sessions. You can devote 2 sessions so that one session you can focus on the theory and then the practice both, right?
Okay. Sure.
One theory, one practice, and you can one purely focus on theory so that everybody understand what it is. And next one purely focus on what the code is, so that we can have two sessions on that, and that should bring us to today. We are already complete in 16, so to 18, 20 it will be. So remaining 4 we'll take some GenAI and probably some practical exams kind of thing, which we would like people to fill in. Those who wanted to certify can get the certification, and hopefully that should be the logical conclusion to what we have done. And I'm very thankful to you for continuing with this approach to learn and to teach. And thanks for the AIML Study Circle for being able to provide the ML guidance to entire POTFs and other members of public. It's a good job. Take care.
So, so yeah, thank you to you and EOTF and everyone behind. So thanks a lot for that too.
So I'll stop here.